So our first speaker is Viktor Mechtcherine.
Okay, thank you very much, Mr. Chairman, for the introduction. Ladies and gentlemen, it's my pleasure to talk to you in this first session. So it's really early in the morning, very unconventional time, at least against the European standards. But we also have an unconventional topic here, right? I mean, maybe not that unconventional as shown in this picture. I will not comment it further. I like this piece of art, but I would rather concentrate on selective deposition technique. And just to get started, let us look at this little graph. If to put it in a positive terms, I would say productivity in construction remains stable. So stable is always sounds kind of good, stability, yeah. But I think it's not what we need, because we do have a lot of tasks in construction, and unfortunately the availability of labor, and I mean labor which can really perform tasks on site, is decreasing. So we have problems. In Germany we have problems, in Europe we have problems. I think everybody knows in the world we have problems with this. So how to tackle the problem? I think the only really good option is to go digital, means to fully automated construction, so towards construction industry 4.0. What we have already, and it is a good news, we have digital planning to some extent, so we have progress here. So it means from CAD and BIM, we get the data we can process further, and we can feed this data to the machine which performs the work. Okay, it's possible now already. And then we need, of course, also the material which does exactly what we need. I mean, the concrete should perform exactly as planned by our algorithm. And this is, I think, the greatest challenge here. Well, if you look at these images, so you can ask what is the idea behind. You do not see any fancy architecture here, nothing of fancy design. So maybe if you compare it to some other presentation, you say, well, it's kind of boring. But this is, I think, what we should keep in mind. Where is the market? And the market is, it looks like this, right? So 90%, maybe 95% of all buildings has straightforward geometries, and we have nothing fancier here. And I think to meet the demands of the market, we should really look on the geometries like this and develop technologies which master this. I'm very excited about the architecture and fancy design. Of course, it's all good, but it can be a game changer on the long term. But in short term, we will deal with geometries, something like this. Okay. Let me introduce our approach. So we, of course, deal first with the data, and then we try to translate this data to on-site mass construction using truck-mounted concrete pump, as shown here, dealing with monolithic cross-sections. We use here concrete which is according to the valid codes, I mean, with large aggregates on all this. And you see that we first start with concrete without any reinforcement, so we replace masonry in the first stage. It doesn't mean we want to stay at this stage, but what I present today, it deals with concrete and not with reinforcement. Well, this is how it looks at the moment in the lab scale. So we have filaments with width of 150 millimeters and height of 50 millimeters. In this example, the big printer, as you shown here, I mean, seen in the previous slide, this truck-mounted pump, it's still to be further developed. So we still have some challenges to control the oscillation of this machine, but in the lab it works all right already. What you see here is the version of the Printhead, which works already pretty nicely. We want to further develop it to achieve even better control of the shape and better surface quality. So you see here an animation which shows that we have some shaping elements additionally here on the side. So, well, the Printhead will look a little bit different, but what you see is the basic kinematics behind this, and this is what we work on now. But I'm not going to talk about the machine as such. I'm going to talk actually about concrete and requirements for printable concrete. If we consider this approach, then first of all we need printable concrete, which also pumpable. So it means that the concrete must be delivered here to the printhead, and it should leave the printhead at a particular flow rate, which we defined as extrudability, and then it should keep the shape, and it should keep a shape also if we put another layer and another layer and another layer. And this is what we call buildability. This is a processing parameters which depends, of course, on the rheological properties, and you can think that for pumpability we need another set of rheological parameters to make it optimum in comparison to buildability, for example. So on the other hand, the processing of concrete also has some effect on the rheological properties, so also this should be kept in mind. So you see the system is pretty complex, so to optimize a system like this, it's quite challenging task. On the other hand, we also know that the rheology of fresh concrete affects the bond between the layers, so, and with this also the properties of hardened concrete. Well, I will not be able to talk about all these issues. I will concentrate myself on extrudability and buildability. And let's start with extrudability. Well, basically, again, the main thing is to guarantee the steady flow of concrete defined according to our data, right? So if it's too little, we have some discontinuity. If it's too much, we have some bulging waves or whatever elements we don't want to have, which means we need to synchronize the motors, all the motors, which move the printhead, but also which deliver the concrete. But the bad news is that these synchronization parameters may depend very pronouncedly on the properties of fresh concrete. So we need to deal with this issue really in detail. Well, mostly we use some kind of a screw extruder, for example, progressive cavity pump is a good example. And we have the formula which describes the flow related to the rotation velocity here. But what we cannot predict here is the force needed to deliver material or energy needed to deliver material. So we're still underway, we're still developing the approach where under consideration of rheological properties we can make prediction like this. What is much easier is to predict this thing for ram extruder. So we have this formula already which consider tribology and rheological property of concrete. But the bad thing is, even if you have this data, you cannot translate it directly to progressive cavity pump extrusion. This is one example. We have here two concretes. I don't want to go here into detail, just let us say here black one and gray one. And we see the tendency for progressive cavity pump in this case is different than from ram extruder. So it means that, again, we need first to understand why it's like this, and then we maybe can predict. What I'm trying to say, at this stage, we are not sure how to deal with the results of measurements of viscosity, yield stress, etc., how to translate them into prediction of energy needed for extrusion process if we use progressive cavity pump. We need at the moment to use approach of direct measurement of flow rate and corresponding energy per unit volume. And from concrete to concrete, it can be different. So we need to investigate it for every separate concrete, and the best with the same equipment you use for 3D printing. So the next one, buildability. Well, basically what it's about is shown here in this slide. You have a wall, and if it's not fit enough, so it just collapse, which we want, of course, to prevent. An elegant approach is, again, here rheology-based. We have here the acting force, which is the gravity. With increasing height, we have increasing here force acting on the first layer, and we compare this force with a very early strength of this first layer, which we can express as the static yield stress. And of course, we know that static yield stress develops in time. So we have here a function. So we have here some parameter which depends on the structural build-up in concrete. And we can measure these parameters using kind of real meter as shown here. Okay, so having this static yield stress and it developing in time, so we can predict, for example, the maximum velocity, which is allowed in particular construction. So knowing also here the length of the element, we can predict it very nicely. But this is not the only thing we need. We also need the minimum velocity, which we can derive from economic availability, printing strategy, and also required bond properties. So we need both here. Well, how to measure this static yield stress? So do not use usual rotational rheometry for this, because what you get there is dynamic yield stress. The static yield stress, you need to start from really zero and slowly increase the shear strain here, and then you get the maximum value of the shear stress, which we define as the static yield stress. Well, if you do it for different ages of concrete, you get also development of this parameter in time. You see that in the first hour or so, it's linear according to the formula suggested by Roussel. And if you wait a little bit longer, then you have effect of hydration, and it becomes nonlinear. So this exponential approach suggested by Pirot is here really good. Okay, this is first good news. Bad news is you have to be very careful about how you measure the things. So it depends really very much on the device you have. For example, the HKMAS 2 rheometer, what we have, is pretty sensible device. And please consider you have here to measure really very stiff consistency. So the concrete is very stiff, which means that if you rely that you always get this shear rate as you defined, here 0.15, so that maybe you are wrong with that. So you see that for some stiff mixes, these ones, yeah, you never reach actually this predefined strain rate. So you measure wrong properties here. So this is what I want to accentuate here. Please always consider all the measurement parameters you get from the measurements and see if you really measure what you want and not what the rheometer delivers just because it's not powerful enough maybe in this case. So we solved, of course, this problem, but because solving the problem, you have first to recognize it. So again, summarizing, we need rheological measurements at the stage when we develop material. Of course, for the quality control, we need some other tests like penetration test, for example, not necessarily with the wicked needle, but something similar. And of course, the ultimate proof is by 3D printing. And this is specifically important if you have more complex geometries, if you go, for example, for... So you need to go also into numerical analysis to simulate the printing process and how the structure develop in time. So you see also here change in colors with change in properties of concrete in time. So I'm not sure that we will have time to see all this video. It just goes like this further and further, layer by layer. What we get as a result later on is some instability issues. You see here that it's less the collapse really of the first layer, but rather buckling here. So typical structural instability, which of course depends very much on the particular geometry we use here. And this is, I think, what we will need to do when we go big with such methods. We need also numerical simulation of the process itself, how the static, let us say, static action of the materials here or the structure is here in the process. Of course, it becomes even more important if we go to inclined geometries. But even if we consider this straight geometry, you see that we can become some issues here with the shape of the individual layers. So it becomes a little bit curved. And again, we need to tackle this kind of a problem. Well, you notice in my presentation, I always say rheometry, rheological properties on all this. Obviously, rheology is really the base science needed to master the processing of concrete materials in fresh state. And we need this control of the rheological properties to go for new technology. It's really absolutely necessary basis. And with this understanding, we started in Germany a collaborative research. This is a called Priority Program by German Research Foundation, which sponsors for 6 years with about 15 million euros a research project in the field of rheology of fresh concrete. There are about 20 groups working on that, and I'm a happy and proud coordinator of this program. And we expect that over the years to come, we will develop a new knowledge on different levels of observation. And of course, it's not just about 3D printing, it's about any rheology-based technology. But of course, we learn here something also for 3D printing. Well, to summarize, we go the way from digital planning to digital construction. So it should be a seamless process which enables really us to improve the productivity very, very much. So we're talking about additive construction here and digital concrete. And just to make the story a little bit more simple to memorize this keywords, I abbreviated to SCDC, right? Okay, thanks to my group and to our sponsors. And last slide, announcement of the conference on rheology of fresh concrete and on self-compacting concrete as well. But self-compacting concrete is by far not the only materials. We will talk a lot of 3D printing as well. It's in September. It's in Dresden in Germany. You see how Dresden looks like. So it's a nice city in September. So please come if you are interested. And that's all for the moment. Thank you.
Thank you, Viktor, for a very nice presentation. I got a question related to your comments on measuring the rheological properties. You say you don't really want to use oscillating rheometer because you'll be measuring the dynamic properties. But you can use it at a very low rate, couldn't you?
Oh, no, maybe it was some misunderstanding. I said I do not recommend to use the rotational rheometry as usual. So then you go up and down, and then going down, you also predict the dynamic yield stress. We use also oscillation methods for sure. You learn a lot from this, but at the moment, actually, I believe that this measurement in the, let us say, stress growth test is more accurate for the prediction of what we need. Of course, again, the question is if we want to use the maximum value of stress, really, because we have already deformation at this, or if we want to stay in the elastic regime, similar to oscillation measurement. So this is, of course, the question, right? But well, nothing against oscillation, not at all.
All right, okay, thank you.
Viktor, well, thanks for the very interesting presentation. Germany is a leading country in this field, I think, with the millions they are spending on this kind of research. We're all jealous about that, I think. Now, I had a question on slide 21. You showed this situation, the printing process and the different colors. Was it 21 or 22? I'm not sure. You had the ground plan of the thing you wanted to print.
This one?
Yeah, this. Oh, it's 22, sorry. And you said the colors refer to different rheological properties. Now you didn't explain. Is this with mixing on demand, or is it all of the concrete mixed at some point? Yeah, and this is due to difference in thixotropic behavior.
Right. It's mixed everything just in one go.
Yeah.
So again, we work with conventional approaches concerning concrete production, and we have nothing fancy like you have. I mean,
yet.
this active rheology control, we don't have this at this stage, even if, of course, in the perspective, we want to introduce some part of these approaches. No, it's just concrete as it is. So it mixed and it's pumped and it placed, right?
Yeah, okay. I have a second question, if you allow me. Well, I think the very interesting aspect in your philosophy is that you use existing equipment, like the pumping equipment with the pumping booms, etc., and then you install the printing unit at the end of the pumping line.
Yeah.
Now, this to me seems critical for, let's say, stability of the end of the boom. What are the developments there? I guess some guys are looking into that as well.
Actually, what I wasn't sure that we get a little bit more time here, but so I haven't prepared the slides for this, but maybe just explain briefly the state of the art of our work. So we had some experiments with a track-mounted pump, and indeed it can be positioned pretty accurately, but there's still some oscillation, some fluctuation, right? And it would only increase if we would intensively pump something for this, yeah? So, but from other fields, we know that it's possibility to control this movement, right? And this is exactly what we are working now on. But we haven't solved it yet, so we cannot present the working system yet. I hope it will come in the next 1 or 2 years, so we will see. So at this stage, we say, okay, we cannot wait. We will further develop the Printhead. And the Printhead is already good enough, I would say, to go on site. But at the moment, we use just the gantry system in the lab to come further. So, and we also built in parallel larger gantry systems that we can have some demonstration projects. But I mean, this pump is not the only machine which we can use. We can also use some other, let us say, conventional machine, just adapt them a little bit and maybe come further towards the automation and construction. So I think we should keep thinking on this. Concerning the money, 15 minutes, it's not my money. I mean, I just get modest part of it. So we are like 20 groups in Germany working. So.
If not, thank you, Viktor.
Okay, thank you.